Okay, so first we begin this problem by we start with saying that the question says that a particle with a mass starts at rest and it moves at a vertical distance um, in the presence of a gravitational field, right? So we have a gravitational field, and for part A, it's asking us to find the work done by the gravitational field or the force when it's at when its y1 is 10 meters, and then it's the change, the y2 is going to be 6 meters, right? So what's the work of this situation when it's moving vertically like this, when it has this change in direction? So for part A, the work simply is going to be, the work we already know is equal to the force in the direction of the displacement, right? So the work, the force is going to be the gravitational force, right, which is going to be mass times gravity, right? And it's, if we see that it's going 10 to 6, it's going from 10 meters to 6 meters, so it's going down, right? So it's going in the same direction as the displacement. So the force is going in the same direction as the displacement, so it's going to be a positive number, right? If it was going in the opposite direction, the force is going in the opposite direction, then it's going to be a negative, right? But it's in the same direction, so it's a positive. And we know that 10 minus 6 is going to be 4, right? That's just that's the displacement. That's the change in displacement. It's 4. So that's how you find the work. It's mg4. Right? Now, part B is asking for the velocity. So what's going to be the velocity? Okay, now to find the velocity, we know that the work is equal to the change in kinetic energy. And so if we plug in what we already know, we know that the work is going to be mg times 4 is going to be equal to the change in the kinetic energy. And that's what this formula is, right? So you just plug in what we know. We know that we start, the initial is, the final is going to be 6, the initial is 10. You plug that in and then you solve for the velocity. When you solve for the velocity, you should get the square root of 80, right, which is around 9 meters per second. It's around there, right? So that's how you do part A and part B. Okay, so now for part C, it's asking us to generalize the equation for any y, right? So to do that, we know that the work has to be equal to the mg to the change to delta y, right? And this, if you actually look at the equation before, that's what we saw before. And this is equal to half of mv squared. This was what the work was equal before, right? But in this situation, the velocity, we, instead of the velocity, we have the delta change in y, right? So that's what these things are equal to, right? So we have here then v squared is equal, so in this equation here, what happened here, we just simplified it, but the masses canceled out. So once the masses canceled out, we get this now, v squared equals 2g to delta y, and then you just square root it, and this is our generalized equation here, right there. V equals the square root of 2g to the magnitude of delta y. Now it's very important to have this as an absolute value, because the delta y has to stay as a positive, because in this situation y1 is bigger than y2, right? We went from 10 to 6, so that would make y1 bigger than y2, so we have to make it, the change would be a negative, so we have to make the magnitude, we have to make it as an absolute value, so it's positive. So that's C. Okay, now D, it asks to find the potential energy associated with the force, right? So this would be the force. The force is equal to negative mg j hat, right? The vertical direction. This is the force, the gravitational force, and this is the potential energy of that's associated with that force. The U equals mgy. Now that's the answer, but this is the answer, but I'm going to show you why that is, okay? So we know that work is equal to U of the initial minus U of the final, right? And according to the theorem, we can equal those two because the work is also equal to mg y1 minus y2, and we know we can put y1 minus y2 here without it being negative, because in this case the y1 is bigger, so it's not going to be negative. And this is going to be equal to right here, as you can see, uy1 and uy2. This is equal to that, because when you distribute it, you're going to get this mg distributed to y1 is the same as this uy1. Mg distributed to negative y2 is the same as this negative y2, right? And now we end up with this, right? This is just to further prove it. We have this u of y1 is equal to mg y1. That's what's basically happening here. We saw there before. And u of y2, the function of y2, is mg y2. That's what happened here, right? And if we subtract them, you get more of this. You get that negative sign. When you subtract them, you end up with this, right? When we subtract them, you end up with this right over here. It's the same thing as that, right? And that's the proving, because this is going to be the force, right? The mg is the force, right? And we just proved that it's the same one. And now this plus c, usually the plus c is added, this plus c is added as a constant, but in this case, when you subtract them, the c's would cancel out anyway, so you don't have to include it in this situation, right? So then sometimes, most of the time, it would look something like this, right, with the plus c, but in this case, since the c's cancel out, it's okay, and you end up with this u of y equals mg of y. That's the potential energy associated with the force. Okay, so now for question E, it's asking us to establish the principle of conservation of mechanical energy. So we know that the mechanical energy is the sum of the kinetic energy and the potential energy, right? So how we're going to show that, right? And how does that look for this problem? So we know work is equal to the change in kinetic energy, and we know that work is equal to the negative change in potential energy, which we saw in the last problem, right? And what that looks like, it looks something like this, right? To expand it more, the kinetic energy of the final minus the kinetic energy of the initial is equal to the kinetic energy, the potential energy of the initial minus the potential energy of the final, right? This is the minus. This is what that minus does. It changes the initial and the final positions, right? Okay, and so according to the theorem, the addition of them should equal this: the kinetic energy of the final plus the potential energy of the final is going to be equal to the kinetic energy of the initial plus the potential energy of the initial. This is the mechanical energy, right? The kinetic energy plus the potential energy, right? And what that looks like in a more expanded form for this problem, it will be this: the half of mv, half of the mass velocity squared of the final, this is referring to the kinetic energy, and plus mg y of the final, this is referring to the potential energy, right? And the same thing over here, this is just referring to the initial, same thing. This is the kinetic, this is the potential, right? And they equal each other, and that is what it would look. This is the mechanical, the conservation of the mechanical energy for this problem.